Otherwise, we might have to watch.
This is unexpected. It's been 3 months since Flight 8 launched back in March. But just yesterday, a set of startling leaked photos, reportedly from inside SpaceX, finally surfaced, offering the clearest evidence yet of what really happened to Ship 34, especially the violent destruction of one of its vacuum Raptor engines. It's raised serious questions about whether the same root problem led to the catastrophic explosion of Ship 36 during its recent static fire. So, what exactly happened? Let's find out in today's episode of Alpha Tech. Around 9 p.m. last night, SpaceX began fueling Ship 36 for a full 6-engine static fire test at the Massey site. The fueling process stretched all the way until 11:01 p.m. But while the ship was still being fueled, it suddenly exploded violently, shattering the stillness of the night. The blast left the SpaceX team in complete shock. Ship 36 was instantly reduced to a shower of twisted metal, with debris flying everywhere. The explosion didn't just destroy the vehicle, it also wiped out key infrastructure nearby, including the static fire stand and adjacent fuel tanks. Thick smoke poured into the night sky and continued to rise for hours. Shortly after the explosion, satellite radar over the Brownsville area quickly detected that a fireball, likely a chunk of metal, had been launched skyward from the Boca Chica facility, flying northwest towards Santa Monica. Fortunately, no one was injured. SpaceX later confirmed the incident in a post on X, saying, "On Wednesday, June 18th at approximately 11 p.m., CT, the Starship preparing for the 10th flight test, experienced a major anomaly while on a test stand at Starbase." They also reassured the public, adding, "There are no hazards to residents and surrounding communities, and we ask that individuals do not attempt to approach the area while safing operations continue." However, SpaceX has not provided any explanation, or even hinted at what might have caused the anomaly. But let's break it down and take a closer look at the slow-motion footage. Right at the moment of the explosion, the light flashes upward from the midsection of the vehicle toward the nose cone, suggesting this wasn't caused by the Raptor engines. That area corresponds to the LCH-4 tank. One possible theory is this. During fueling, Starship is loaded with liquid methane and liquid oxygen, both ultra-cold and highly flammable when mixed. If there was a leak in the LCH-4 tank, or the fuel lines running through the midsection, where the main tanks are located, methane and oxygen could have escaped, mixed, and ignited. But to know for sure, we'll have to wait for an official answer from the company. Now, let's turn to another big piece of news that just came in. Earlier this month, the FAA officially closed its investigation into Starship Flight 8 after confirming that SpaceX had implemented 8 corrective actions to prevent future propellant mixing issues. Just when it seemed like the case was closed, someone came forward with these leaked photos. Take a look. They're now spreading across X like wildfire. Behind-the-scenes evidence from Ship 34's Flight 8 is revealing a whole new level of detail. Some of the angles match what we saw during the original broadcast, but others expose key moments that the public never got to see. One photo in particular has drawn massive attention. It shows a vacuum Raptor engine violently torn apart, appearing to have exploded even before separating from the vehicle. In that image, the engine's nozzle is split right down the middle, with the upper section shredded and fully exposed. The protective casing is completely gone, revealing internal components that should have been shielded from such extreme forces. You can even see fragments of metal scattered across the frame, painting a chilling picture of just how catastrophic that moment truly was. The 2 photos above show what happened moments earlier. While the quality is a bit blurry, it's clear enough to suggest there was some kind of fuel leak in the left image. In the right one, what appears to be smoke or vapor, dark in color, seems to be coming from the sea-level engines, possibly from leaking propellant being vented out. This moment perfectly matches what was captured by the ship's onboard camera at T+7 minutes and 45 seconds, right when a burst of orange flame first appeared in the engine bay, along with the heat from engine combustion. Less than 20 seconds later, things quickly started to go downhill. By T+8 minutes and 5 seconds, 1 vacuum engine and 3 sea-level Raptor engines had shut down. At the same time, the alt-flap camera showed a violent burst of white smoke coming from the engine section. The ship began to wobble and lose control, 146 kilometers above the ground, flying at an insane speed. It kept tumbling. Then, at T+9 minutes and 3 seconds, SpaceX cut the live stream. even though the ship hadn't exploded yet. The onboard camera was still running, but they chose not to show what happened next. The leaked photo of a Raptor vacuum engine, ripped off and obliterated, hints at the violent end that followed shortly after. According to experts, the problem likely started with that detached Raptor vacuum engine. Once it exploded, it may have scattered debris in all directions, damaging several nearby engines almost instantly. In this case, it's possible that SpaceX tried to re-establish contact with Starship before triggering any flight termination protocols. But, with the vehicle completely out of control, the system's onboard flight termination system likely kicked in automatically after the signal was lost, ensuring the craft broke apart in a controlled way and preventing uncontrolled debris like what happened during Flight 7. The most likely root cause of the Starship loss was traced back to a hardware fault in one of the Raptor engines, which led to an unintended fuel mix and ignition. This is especially dangerous because if the fuel mix between methane and oxygen isn't just right, say too rich in methane or too much oxygen, the combustion can become unstable. This phenomenon, known as combustion instability, causes pressure waves to ripple through the engine's combustion chamber. These violent oscillations can spike local temperatures or push pressure beyond design limits. And if there are any flaws in the material, like tiny cracks or subpar welds, those weak points can quickly give out under such extreme stress, leading to leaks or even structural failure. Once the structure breaks, liquid methane and oxygen can escape and ignite almost instantly, resulting in a full-blown explosion. Since that test flight, SpaceX has been conducting extensive ground testing to better understand the issue, including over 50 long-duration Raptor firings at their McGregor facility. To address the problem in future flights, the upper stage engines will now be reinforced with additional preloads on key joints, a new nitrogen purging system, and improvements to the fuel venting system. These enhancements build on earlier fixes introduced after Flight 7, which saw early engine shutdowns caused by harmonic vibrations. While engine performance during Flight 9 was generally more stable, the mission ran into a different problem, a leak in one of the fuel tanks. That caused a pressure drop, which starved the engines of propellant, eventually leading to Ship 35 losing control. It's like patching one hole only to find another, but that's exactly how the Starship development process works. Fail fast, learn fast, fix fast. Every time something goes wrong, they quickly roll out updates and improvements. The goal? To keep refining the vehicle until it meets the FAA's strict safety requirements, and us as too, especially with that $2.9 billion contract for the Starship human landing system on the line. But it seems SpaceX's efforts haven't impressed everyone. Take Will Lockett, for example, a former engineer turned journalist who frequently covers SpaceX and Tesla. In a recent controversial article, he claimed that, dig a little deeper, and it's evident that SpaceX has hit an impasse. According to Lockett's analysis after Flight 9, the booster is both too heavy and too fragile. And if that's true, SpaceX engineers could be facing a serious dilemma. The super heavy booster and its engines need to be heavily reinforced to survive a landing like that, especially if it's going to be reused as planned. But doing so would add so much weight that it defeats the whole point, Lockett wrote. Meanwhile, the upper stage did show some progress. It reached space and achieved near-orbital speeds, but just like the last two flights, it suffered a propellant leak. This time, instead of exploding right away, it spun out of control and disintegrated in the upper atmosphere. The fact that yet another propellant leak caused catastrophic failure suggests they have a systemic stress propagation issue, Lockett continued. After Flights 7 and 8, SpaceX reinforced the fuel lines and the structural mounts around the engines. But now, a more distant component has failed, implying the stress is simply shifting to other, weaker parts of the vehicle. But, in some respects, he's got a point. Reusability is the core purpose of Starship. If both the booster and the upper stage can safely fly again and again, the payoff is huge, saving SpaceX and its customers precious time and money that would otherwise be spent building new hardware from scratch. Still, to judge the program fairly, we need to zoom out and look at the broader journey, not just a single setback. Currently, after the incident with Ship 36, SpaceX has faced quite a bit of criticism, but in many ways, that pressure is also pushing them to go even further and succeed even more in the long run. Yes, Starship Flight 10 won't be happening this month. In fact, The timeline may even slip into early August. Or maybe not. That's because Ship 37 has now emerged as a strong candidate to replace its ill-fated sibling, Ship 36. Just a few days ago, on June 16th, Ship 37 was moved to the back processing stand inside Mega Bay 2. It's still missing about 90% of its heat shield tiles, but as of now, roughly 70% of the ceramic shielding has been installed. And just yesterday, one of the vacuum engines was spotted being transported into Mega Bay 2, likely intended for Ship 37. That's a clear sign that work is ramping up again, and that preparations for the next historic launch, Flight 10, may not be delayed for too long. If successful, this would be a powerful testament to SpaceX's relentless efforts to refine and accelerate its Starship program, highlighting real gains in both launch cadence and hardware production. In fact, SpaceX seems to be charting a strong, steady path for future missions. Looking toward the end of 2025, the momentum could become even more apparent. So far this year, SpaceX has launched 3 Starship missions. If they keep up this pace, we could see at least 7 more launches before the year is out, marking a major leap in flight frequency compared to last year. And that's not even counting SpaceX's ambitious push to rapidly expand launch capabilities at both coasts, with a bold vision of flying hundreds of Starship missions per year from Florida alone. Big progress is already underway at Launch Complex 39A, and a packed manifest of 76 missions is planned for Launch Complex 37, which is being transitioned from United Launch Alliance to SpaceX. Reaching that ambitious goal will require a steady launch rhythm, at least 10 Starship flights per month. But to get there, SpaceX first needs to build on the foundation of 2 back-to-back successful flights. And the upcoming Flight 10 is shaping up to be a critical milestone in that journey. We'll have to wait and see how it all unfolds and what kind of impact it could have on the space industry. If you believe in the vision behind Starship and the significance of Flight 10, type "Go Starship" in the comments below. Thanks a lot. From a deserted beach to the world's biggest rocket paradise in just 9 years, SpaceX is building Starbase at an incredible pace. That's no exaggeration. Starbase is being built by a team even more skilled than those who built the Great Pyramids of Egypt, one of humanity's most iconic engineering feats. And with that level of talent, it's no wonder the transformation here is accelerating. SpaceX is now aiming higher than ever, upgrading the production site to churn out up to 1,000 Starships a year, and expanding the launch site to handle hundreds of flights every week. This is the clearest sign yet of Elon Musk's full commitment to Mars, and it's left even NASA's Artemis team completely stunned. So, what bold changes have been happening at Starbase lately? For years, NASA has regularly sent oversight teams to Starbase as part of the Artemis program, not just to check on Starship's progress, but to independently assess the pace, safety, and feasibility of its development. Every visit brings surprises. Things move fast at Starbase, often transforming so quickly that even just a few months between visits can feel like stepping into a whole new facility. Most recently, the team was stunned to discover that the iconic high bay, once the heart of early Starship production, was gone. This was the building where the first prototypes were assembled, a key landmark that symbolized how far Starbase had come. But by March 2025, dismantling was already underway. Crews didn't just take it down, they cleared everything, down to the foundation itself. Not a trace remains. Taking its place is the much larger Gigabay, a next-generation factory built to scale up production and support a full Starship fleet, paving the way for future Mars missions. We can clearly see that SpaceX has cleared not just the old high bay site, but also pushed the cleanup all the way to the current edge of the Star Factory. To do that, they even dismantled part of the Star Factory itself, a bold move that hints at major expansion plans. It looks like Gigabay might be built right next to the main factory, or even directly connected, making it easier to move massive components like ship payload bay sections and Raptor engines between buildings. If that's the case, the size and scale of this new facility could be absolutely massive. And that would make perfect sense. Elon Musk has already announced that this new infrastructure, combined with the 2 nearby megabays and another factory currently under development in Florida, will have the capacity to produce 1,000 Starships a year. That's about 3 Starships every single day. Although SpaceX hasn't officially released specs for Gigabay at Starbase, the cleared area gives us a solid estimate. The structure is expected to stand around 392 feet tall, with the bulk of that height, roughly 370 to 380 feet, dedicated to the vertical assembly and integration of Starships and super heavy boosters. The top floors, about 12 to 22 feet, would likely serve as workspaces and meeting rooms to support day-to-day operations. Inside, Gigabay could feature up to 815,000 square feet of working space. That's nearly 10 football fields. With 24 dedicated work bays, SpaceX would be able to handle multiple Starships and boosters simultaneously, pushing production capacity far beyond what Megabay 1 and 2 can currently support. This setup would allow up to 24 Starship or Super Heavy prototypes to be worked on at the same time, a huge leap from current capacity. Right now, Megabay 1 and Megabay 2 can each support only about 5 vehicles at once. That's why Elon Musk feels confident making such a bold production claim. With Gigabay in the mix, SpaceX isn't just scaling up. They're aiming to mass-produce Starships the way Tesla builds cars. Building something like this doesn't happen overnight. SpaceX hasn't officially announced when construction on Gigabay will begin or end, but with High Bay now fully cleared, work on the new facility could kick off as early as late June or July. FAA documents for the Gigabay project in Florida suggest a 4-month construction timeline, so the Starbase version might follow a similar schedule. If everything goes smoothly, Gigabay could be done by November this year and fully operational by early 2026. That's way ahead of the Florida facility, which isn't expected to be ready until August 2026. So, what do you think? When will Gigabay at Starbase go online? Drop your thoughts in the comments. To support the massive Starship production ramp-up, especially when the Mars transfer windows open between 2030 and 2035, SpaceX needs to launch frequently and fast. That's why they've built a second launch pad at Starbase. Launch Pad B at Starbase broke ground in January 2024, and it's a big step up from the original. This new pad comes with upgraded chopsticks, now strong enough to catch not just the booster, but Starship itself. It also features a reinforced flame trench to better handle the brutal heat and force from liftoff. With 2 pads running, SpaceX could soon double or even triple its launch rate, exactly what's needed for future Mars cargo missions. And to sustain that kind of pace, the durability of the launch infrastructure becomes absolutely critical. Because, when all 33 Raptor engines on the Super Heavy ignite, it's absolutely brutal. Take Flight 9, for example. The booster quick disconnect system, arguably the most sensitive and complex part of the entire launch mount, took a serious beating. It wasn't just scorched on the outside, the heat burned deep into its internal components. Some areas even showed cracks, and parts of the casing and joints appeared to have partially melted. All of this only highlights how essential Launch Pad B really is. With its more advanced thermal protection system, it's designed to handle this kind of extreme environment far better. At this point, Launch Pad B is nearly complete. Its orbital launch mount, or OLM, is totally different from Pad A's. Instead of a round base, Pad B's mount is square, with a circular insert in the middle that fits perfectly with the Super Heavy booster. It's welded onto 4 support legs embedded into the flame trench walls, a major upgrade from earlier reports that said it would be mobile. This fixed design adds serious strength and does a much better job absorbing the insane 230 tons of force from the 33 Raptor 2 engines, and even more when Raptor 3 engines come into play, which are expected to push that number closer to 300 tons. This new protection system is so advanced, even NASA's Artemis teams had to take notice, and maybe feel a bit jealous. Why? Because their own rocket, the SLS, actually damaged its launch pad on the very first flight. During the Artemis I launch in 2022 from Pad 39B at Kennedy Space Center, the insane 8.8 million pounds of thrust from SLS scorched the zero deck, the platform directly beneath the engines. Paint was stripped, parts were burned, and key pneumatic lines carrying nitrogen and helium were damaged, triggering false oxygen sensor alarms. The blast pressure even blew open the elevator doors on the launch tower, knocking the system offline for months. Debris from the rocket, including solid booster throat plugs and thermal insulation material from Orion, was also found scattered around. NASA wasn't even sure whether some of that damage came from the launch or from Hurricane Nicole just days earlier. All right, back to the story. SpaceX's new OLM was fully installed just last month. As for Makezilla, that beast has been solid since day one. What SpaceX has really been testing is the chopsticks, especially the new ones on Pad B. Last month, they did a load test with 4 giant water bags, each over 100 tons. Elon Musk even joked that they were big balls. The test? A total success. Right now, only Pad B has chopsticks capable of catching Starship, thanks to its slimmer landing rail lips designed specifically for that task. The flame trench under Pad B has also made serious progress. Groundwork began on January 13, 2025, hitting bedrock by early February. Concrete was poured in March, and the first wall sections went up by March 21st. By May, most of the deluge pipes and sidewalls were already in place. The only thing still under construction is the deluge tank farm, with new pumps, control modules, and stairways recently delivered to complete the setup. All signs point to Pad B being operational by the end of this year. Perfect timing, because as Elon Musk said on X, later this year, if fate smiles upon SpaceX, the ship will be caught by the tower, just like the booster. But that excitement? It's just the start. A new Starship launch pad is rising, not in Texas, but deep in Florida on ULA's old turf. This isn't just construction, it's a power shift. SpaceX is moving in where ULA once ruled. On the morning of June 13th, a loud explosion echoed across Launch Complex 37B at Cape Canaveral Space Force Station, Florida. It wasn't an accident, it was a planned demolition to bring down the mobile service tower, the fixed umbilical tower, and 2 lightning towers. The goal? To clear the site for SpaceX, which is expected to lease the land and transform it into a future Starship launch site. This pad was once home to ULA's Delta IV rocket, but after its retirement in April 2024, the complex became obsolete. SpaceX had shown interest in the area for some time, and with support from Florida officials, the transition is now underway. The handover suggests ULA is adjusting to a changing industry, but it also hints at deeper struggles. Scaling back infrastructure may signal financial pressure or strategic retreat. One thing's clear. As SpaceX expands, the balance of power at Cape Canaveral is shifting fast. This shift has also raised concerns within NASA, especially considering ULA's long-standing contributions to the agency's Launch Services Program, LSP. For years, ULA has reliably launched scientific payloads, satellites, and spacecraft using vehicles like the Atlas V, Delta IV, and more recently, the Vulcan Centaur, all without relying on the space shuttle or other heavy lift systems. More importantly, while ULA's role may not be as prominent as SpaceX's, it still plays a vital part in NASA's Artemis program, which aims to return humans to the moon. Any signs of downsizing or instability could ripple through mission planning, and that's not a risk NASA can take lightly. But from another angle, SpaceX's growth is actually a win for NASA. As the agency's biggest and most reliable private partner, any expansion on SpaceX's end means more capability for future missions. Right now, the company has 4 launch towers, 2 at Starbase in Texas, 1 at LC-39A, and the newest one coming together at SLC-37 in Florida. This network gives SpaceX valuable redundancy. If one site, say Pad A at Starbase, goes down for maintenance or upgrades, Pad B can keep operations going. The same goes for LC-39A and SLC-37, which can back each other up and keep schedules running smoothly. More importantly, those 2 Florida pads are just minutes from NASA's Kennedy Space Center. That proximity makes it easier for NASA teams to work hands-on with SpaceX, from payload integration to real-time launch oversight. It strengthens the public-private partnership model of Artemis, letting NASA leverage commercial infrastructure instead of pouring billions into new facilities. Looking ahead, with 2 Starship pads on the East Coast, SpaceX can offer missions at a fraction of the cost, tens of millions per launch versus SLS's $2 billion price tag. That opens the door for NASA to offload secondary missions like CLPS or gateway modules to SpaceX, freeing up SLS for only the most critical flights. SpaceX has just ignited a firestorm of debate after revealing its brand new grid fins design. The number of grid fins on Super Heavy Block 3 is being cut from 4 down to just 3. But what's really stirring the pot? It's the fact that all 3 fins are now asymmetrically placed. Some people say this could mess with the rocket's aerodynamics, while others think it might actually help stabilize the booster. So, what's the real story behind this bold new design? Just a few weeks ago, during a Mars presentation, Elon Musk shared quite a lot about the latest versions of Starship and Super Heavy. But the thing that really caught everyone's attention was the booster's appearance. It's now equipped with a brand new hot staging ring, and Musk mentioned that the struts on this ring help the exhaust gases escape more easily during the hot staging process. And if you look closely, right below the hot staging ring, you'll notice another big change. There are only 3 grid fins now instead of 4, and they're placed asymmetrically at 90, 90, and 180 degrees. However, Musk didn't give any explanation at all about this change, and that's what's got people talking. Will it actually work well, or could it mess with the booster's performance somehow? To understand what's really going on, let's back up for a second and talk about how these grid fins actually work. At first glance, they might look like oversized metal waffles stuck to the rocket, but they're way more important than they look. These grid fins are what help steer and stabilize the booster during its high-speed fall back to Earth. Inside, a hydraulic actuation system, powered by high-pressure fluid pumps, drives precise rotations of the fins, allowing them to tilt and adjust the rocket's trajectory. They don't work like traditional air brakes. Instead, they focus on control and stability, using fin rotation to guide the Super Heavy booster to a pinpoint landing. When they're lined up with the wind, there's barely any drag. But the moment they start tilting, that's when they bite into the air, creating aerodynamic torque that lets the booster twist, turn, and stay on course. Each fin rotates around a single axis, but it's not about what they do alone. It's how they move together that really gives the rocket full control. To put it simply, in the current versions of Super Heavy, the booster is equipped with 4 grid fins, arranged in an alternating pattern of 120 and 60 degrees around the top of the booster. This symmetrical layout allows for effective and relatively simple control over the 2 main axes of motion: pitch, tilting up and down, and yaw, turning left and right. To control the rocket's pitch, 2 fins positioned opposite each other, let's say one on top and one on the bottom, relative to the desired direction, can tilt in opposite directions. For example, the top fin tilts up, the bottom fin tilts down. This creates torque that pitches the rocket nose up or down. To control yaw, or the left-right movement, the 2 side fins can also tilt in opposite directions. That generates the sideways force needed to steer the booster left or right during descent. Okay, that's how the traditional 4-fin setup works. It does the job really well. So, why did SpaceX drop one of the grid fins? Instead of 4, the latest Super Heavy booster uses just 3, arranged asymmetrically. Sounds strange, right? No more perfect symmetry, no more opposite pairs. But here's the clever part. In this new setup, each fin doesn't just do one job, it helps control both pitch and yaw at the same time. Let's say the rocket needs to pitch up. The 2 fins sitting 90 degrees apart can tilt together to generate upward lift. Meanwhile, the 3rd fin, the one sitting at 180, steps in to balance things out, or add a little extra force. It's a more coordinated dance, but it still works. And for yaw, or turning left and right, same story. The fins move in sync, each contributing part of the needed force. Even roll control, rotating the booster around its axis, can still be achieved by turning all 3 fins in the same direction. No symmetry, no problem. You just need smarter software to keep it all in tune. So with just 3 fins, SpaceX still gets full control, pitch, yaw, and roll without sacrificing performance. And that's not even counting the weight savings. Dropping just 1 grid fin cuts a huge amount of mass. According to SpaceX's design, each fin is around 7 by 3 meters and weighs about 3 tons, nearly 20 times heavier than a Falcon 9 fin. That's the trade-off for handling Super Heavy's insane size and re-entry forces. So shedding that weight means less work for the Raptors on the way up, and less impact on Mechazilla when catching it on the way down. Pretty smart move. Interestingly, Super Heavy's grid fins still stick to the old-school design, welded stainless steel, unlike Falcon 9's fins, which evolved from aluminum to titanium over time. This difference highlights a core design philosophy. Why stainless steel? The answer's pretty convincing. It's 15 to 20 times cheaper than titanium. At current prices, 3 tons of 304 stainless steel cost around $10,000. And if you're mass producing like SpaceX, that drops to just $7,000 to $8,000 per fin. Here's the kicker. Elon Musk is aiming to build 1,000 Starships a year. That means 4,000 grid fins annually. So, removing just one fin per booster, that instantly slashes production time and saves millions of dollars. It's also faster and easier to build, thanks to welding. No need for complex forging like with titanium. Plus, stainless steel handles heat way better. 301 grade. Steel keeps its strength up to around 1,550 degrees Fahrenheit, compared to just 625 degrees Fahrenheit for grade 5 titanium. And that's not all. SpaceX didn't just change the number of fins or the material they're made of. They also moved them. Instead of being tucked inside the interstage section, like on Falcon 9 or earlier Starships, the grid fins are now mounted right onto the methane tank. So, yeah, in general, removing one grid fin isn't just a random tweak. It's a calculated move, part of a bigger picture, a bold design philosophy built around low cost, fast manufacturing, and extreme reusability. But everything we've talked about so far is still just theory. Of course, SpaceX engineers have studied how the fins performed on past flights and carefully crunched all the data before locking in this new design. But we'll still have to wait a bit longer to see how Super Heavy really flies with just 3 fins. Right now, the first flight using the upgraded Block 3 version of Super Heavy is expected sometime in late 2025 or early 2026, possibly with Booster 19 or 20. These boosters are likely being built from scratch to match all the Block 3 upgrades, like a stretch structure, new Raptor 3 engines, and other design tweaks. But hey, that's just an educated guess, based on SpaceX's naming patterns and production trends. They could easily jump ahead in numbering, like Ship 39, which was spotted with a completely new nose cone layout and welding method, or Booster 20, which might mark the clear shift into the V3 era. Alright, grid fins are just one small piece of the bigger Starship V3 puzzle. Now, let's zoom out and take a look at the full picture. Do you remember when SpaceX once said that Starship version 3 would be around 150 meters tall when fully stacked? Well, in the latest presentation, that number quietly disappeared. Instead, Elon Musk just called it the future Starship, now listed at 142 meters. So, maybe the 150-meter version is being saved for Block 4. In this updated version, the booster will be 81 meters tall and the upper stage, Starship, will be 61 meters. That lines up perfectly with Musk's mention of 4,000 tons of propellant and 10,000 tons of liftoff thrust. Interestingly, the upper stage is now shorter than the 69.8 meters previously planned for V3 back in 2024. Honestly, I'm glad they made that change. The old design looked too tall and bulky. The longer the vehicle, the more it's affected by harmonic resonance. And this shorter profile also fits with Elon's claim that the future Starship will be about 20% more efficient than the current version. And it's not just size. This future version also comes with major design upgrades across the board. Like Elon Musk mentioned on X, Starship will have 42 engines. That's 33 on the booster and 9 on the upper stage. Right now, the upper stage is equipped with 3 vacuum-optimized Raptor engines, but eventually, that number is expected to go up to 6. At first, that might sound like it would put more stress on the hot staging ring due to the added thrust, but that's not necessarily the case. In fact, having more engines could actually improve control during hot staging. With just 3 vacuum Raptors, the exhaust flow isn't evenly distributed during separation. All 3 have to fire at once, and their plume can hit the grid fins directly, which could cause heat damage or uneven forces. But with 6 Raptor 3 engines, Starship could choose to ignite only 2 during the initial hot staging phase. These could be strategically positioned to minimize impact on sensitive parts while still providing enough thrust to separate cleanly. Then, once the stages are safely apart, the remaining engines can kick in. This staggered ignition approach would make hot staging cleaner, safer, and more efficient. Speaking of hot staging, remember at the start of the video I mentioned the new design of the hot staging ring? Let's call this Ring version 3. It's a complete upgrade in terms of performance compared to the old design. In this new version, the support struts are no longer part of a separate ring that gets bolted on right before launch. Instead, they're directly integrated into reinforced hardpoints on the booster structure itself, meaning there's no standalone horizontal ring underneath anymore. In practice, that means the ring is now a permanent part of the booster. Setup time on the launch mount is reduced because there's no separate piece to lift and install. And in flight, there's no need to jettison it, eliminating another piece of hardware that would otherwise need to be recovered or discarded. Part of the reason it doesn't need to be jettisoned is because it's also much lighter than before. The old ring weighed about 9 tons, but the new one is estimated to come in at just 7 tons. The more open design also helps avoid certain risks. For example, during Flight 9, SpaceX used a modified hot staging ring, where part of the vent cutout was intentionally blocked and sealed. This tweak caused the exhaust from Starship's engines to push the booster at a calculated angle, reducing the amount of propellant needed for the kick maneuver and improving efficiency. It was a clever trick, but in the end, it didn't offer a huge advantage compared to just integrating the structure fully into the booster and cutting the weight. In short, these refinements, from grid fins to the redesigned hot staging ring and adjusted vehicle size, aren't just isolated upgrades. They are part of a bigger strategy tied to Mechazilla's demands and Starship's ultimate goal, carrying more payloads more often. The shift from Block 2 to Block 3, along with hints of a future 3-fin design, shows how SpaceX constantly adapts and improves. And at the core of it all, these changes to Super Heavy's grid fins help unlock Starship's full potential, paving the way for regular, low-cost access to space and, one day, a sustainable human presence on Mars. SpaceX Starship's efforts to carry payloads into orbit have a big problem. Specifically, its door can't even budge. This is not the first time the company has installed Starlink simulators for Starship version 2, 3 times, but the hopes of testing have all exploded with the ship in midair. That's crazy. So, why SpaceX can build the largest reusable booster but can't open the door? What's the solution? Last month, Starship Booster 14 luckily went almost as planned. After performing the separation process, it entered the atmosphere at an unexpected angle and made an uncontrolled descent, exploding at T+616. But what is worth mentioning here is that the upper stage of Starship S-35 recorded the third vehicle exploding from Starship version 2. According to Musk's announcement on X, the cause is not uncommon with another fuel leak, and from what can be seen on SpaceX's live video, the signs of leakage can be seen both inside and outside the ship, which cannot be denied. But it cannot be denied that the ship was able to travel further than the 2 ships that exploded before, far enough to see more problems. Most importantly, Payload door got stuck at the 18-minute mark instead of opening and performing the operation of pushing the 8 Starlink dummy satellites out as planned. We were looking forward to this operation with a PEZ dispenser. It was planned to be like dealing cards in a casino, only the cards of the Starship seemed much bigger and heavier. So, what was the real reason for this immobility? It must have gotten stuck and couldn't move. The drive system for the door didn't work properly during this process. Let's explain. Do you remember the previous Flight 3? The payload door in Starship version 1 was recorded as a success, even though it didn't open completely. The Starship above version 2 was upgraded, but the result was not as good as its old version. Therefore, the main reason to mention first is the new design of the door. Instead of using structural bars for reinforcement, the Starship payload door has now been replaced with a less permanent installation. The structure includes a piston inside the ship that is connected to the accessories on both sides of the door and pulled up to open the door, which will tilt inward and open the passage for Starlink. Next, there is the problem of losing control of the tilt, making the Starship unstable. The S-35's fuel leak has led to a loss of pressure and loss of attitude control. The inability to maintain a stable attitude in orbit causes both the payload door and the satellite deployment system to fail to function properly. In addition, have you noticed that dense ice particles are floating in the cargo hold? The appearance of these ice particles is unusual, and it is not in the right position, the cause of which is none other than a fuel leak. But the problem is that its appearance has further reinforced the problem of the payload door not being able to deploy. Because if any liquid leaks into the cargo hold, It can damage the pressure balance or cause unexpected resistance in the door mechanism. Other environmental stresses also have a significant impact. Due to the temperature change in space when one side is exposed to direct sunlight, while the other side is freezing cold. The high temperature difference can cause parts to expand or contract, causing the joints to lose their joint integrity. This makes me even more skeptical about whether the Starship's welds are really effective in the space environment. Do you have any other thoughts on this issue, or any other causes of this jamming? Please comment and let me know. We look forward to your contributions. Now, what solutions to solve these problems? The most urgent priority is to strengthen and reinforce the structure around the Starship cargo door area. Adding stronger reinforcements will play a key role in ensuring the stability and safety of the door throughout the entire flight process, from launch to re-entry. However, these reinforcements not only need to have high mechanical strength to withstand large impacts, but also need to be designed to be compatible and flexible with the drive system to ensure the door opens and closes smoothly and accurately. The ultimate goal is to develop an optimal design that allows the door to operate reliably and efficiently, even in the harsh environmental conditions of space, where extremely low pressure and constant temperature changes can severely affect the operating mechanism. Next is the clamshell payload door design, known from the early days of the Starship program. The clamshell payload door opens into a massive cargo bay promised in early Starship designs. The design is reminiscent of the payload doors on NASA's retired space shuttles. The system is designed as an integrated structure in which the payload, including satellites or space vehicles, is installed directly inside before launch. The clamshell is then sealed and remains sealed throughout the launch to protect the payload from atmospheric pressure, vibrations, and other harsh environmental factors. Once the spacecraft has reached its target orbit and deployment conditions are ready, the payload deployment process begins. First, the clamshell door is precisely opened using a remote-controlled actuator system. Immediately after, the payload transfer mechanism, an intermediate mechanism connecting the payload to the spacecraft body, tilts at a pre-calculated angle, helping to guide the payload onto the correct separation trajectory. At the appropriate time, the payload is released using a dedicated separation mechanism that has been specifically designed for the requirements of each mission. In the case of a flight carrying multiple satellites or payloads, Starship can use an additional rotating mechanical system, usually an integrated turntable, to change the position of the payloads. This allows each satellite to be separated in a specific order, while ensuring that the distance between the objects after deployment is optimal, avoiding collisions. Once the entire payload has been successfully separated and past the impact area of the clamshell, the system will perform a confirmation using sensors or tracking data. When all conditions are guaranteed, the clamshell door will be safely closed and prepared for the next phase, that is, bringing Starship back to Earth. Equally important, the fuel leakage problem needs to be thoroughly solved. Starship version 2 has exploded in mid-air 3 times due to fuel leakage problems. S-33 on Flight 7 was completely lost 8.5 minutes into the flight and exploded shortly after over the Turks and Caicos Islands. On Flight 8, S-34 exploded even earlier when a strong signal appeared on the tail of Starship, causing some Raptor engines to fail, leading to loss of attitude control and eventual loss of contact with Starship. A leak in the fuel tank was also confirmed on S-35, leading to a drop in pressure and failure to provide enough fuel to the engines. However, early in the flight, after complete separation from B-14, leaks were seen right on the Raptor 2 engines. As of T+0823, a small area on the vacuum Raptor was seen showing traces of a small flare. Shortly after, at 9:36, a leak was also seen on the hull of S-35. So the most practical way is for engineers to add secondary protection or reinforcement to vulnerable components such as fuel tanks, manifolds, and critical piping systems to increase the durability of these vulnerable components. In addition to structural and material improvements, SpaceX could also research, design, and deploy an intelligent automatic sealing mechanism that would be able to quickly detect the potential leaks in the system and immediately take sealing measures to prevent the leak from spreading or seriously affecting the mission. Although developing such a system would require advanced technology, large resources, and complex testing if successful, it would significantly improve the safety and reliability of Starship during flight, especially on long-duration missions or in harsh space environments. This is necessary as the importance of this small payload door deployment shouldn't be underestimated. Starship is an efficient and cost-effective platform for building and maintaining satellite networks, including the expansion of SpaceX's Starlink constellation. Successfully demonstrating the ability to deploy multiple satellites in a single mission will strengthen the role of Starship. The payload contracts will be extremely large because the number of payloads Starship can transport in just one flight has enhanced the convenience and cost savings that companies and organizations desired. The satellites being modeled on S-33, S-34, S-35 represent SpaceX's new V3 satellites. Currently, Starlink satellites are launched on Falcon 9 rockets. However, the next-generation V3 satellites are expected to be significantly heavier than the current V2 mini spacecraft. So only the incredible payload capacity of Starship could be suitable for missions to deploy this version of the satellite. SpaceX has announced plans to deploy 60 V3 satellites per Starship launch. This would add an impressive 60 terabits per second of capacity to the Starlink network. Each V3 satellite would provide 10 times the downlink capacity and 24 times the uplink capacity of a V2 mini satellite, significantly improving the overall performance and capacity of the Starlink network. However, we won't have to wait long. In recent days, we have been able to see the latest developments with the upcoming 10th flight parts. B-16 has completed its static fire test with all 33 Raptor engines. It has now been transferred to the production facility. The payload system test will be tested next on the 10th flight, and we believe with SpaceX's experience, with what they have collected from previous launches, flight number 10 with S-36 will be successful. By the way, the problems affecting the payload door on S-35 are not a small problem. The remedies need to be carefully considered to avoid such stuck cases in the future. Just think about it. If in the future, when Starship is performing a mission to launch any payload or just deploy their Starlink satellites, the stuck problem suddenly occurs. Just thinking about it is funny, right? It costs tons of fuel to launch, then it has to return to the mission that is still open, of course, at the time when it can be safely reused. The contract cannot be canceled, of course. Another launch takes place and a corresponding amount of fuel, a small amount of money is consumed, all doubled or tripled, even more than the initial cost in just one mission. So, this is a serious issue. SpaceX should consider it carefully and make better adjustments. However, do not forget how glorious SpaceX's development history is, so, no matter what, we trust and wait for their solutions. It's all just a matter of time. Maybe now, a few weeks, a few months, a few years. We who are following the information can only continue to wait and hope. When you hear nuclear energy, what comes to mind? For many, it's the dark side, nuclear weapons, war, and destruction. But scientists are rewriting that story. That dangerous power is now being harnessed for ambitious goals, powering submarines, generating electricity, and even propelling rockets into deep space. And the next big leap, nuclear rocket engines. NASA's been chasing this technology since the mid-20th century, and they believe it could outperform even the most powerful chemical engines, like mighty Starship's Raptors, when it comes to specific impulse, fuel efficiency, and durability on long missions. Imagine cutting a trip to Mars from 6 months to a few weeks. That's something no current rocket can pull off. Sadly, Trump's new budget cuts are putting the future of this game-changing project at risk of being scrapped entirely. So, what exactly is this nuclear engine? How does it stack up against SpaceX's Raptor? And can it survive the political shift? In a newly announced round of budget cuts from the Trump administration, NASA's funding will drop from $24.8 billion this year to just $18.8 billion by fiscal year 2026. One of the biggest casualties was the termination of the experimental nuclear thermal rocket engine program. NASA's partner on the Draco mission, the Defense Advanced Research Projects Agency, has confirmed it's shutting down the project due to the cuts, and transferring the technology to other agencies. It's a real loss for anyone following this project, as it held enormous promise compared to traditional chemical engines. So, why is it better? To understand that, let's rewind and see how traditional rocket engines got their start. Traditional chemical rocket engines, especially the liquid-fueled kind, have long been the backbone of modern space missions. The idea dates back to 1903, when Russian scientist Konstantin Tsiolkovsky first proposed the theory behind them. Later, American physicist Robert H. Goddard, often considered the father of modern rocketry, brought that theory to life. Building on Tsiolkovsky's ideas, he developed a working engine, one that he would spend more than 20 years refining. In 1926, Robert Goddard launched the world's first liquid-fueled rocket in Auburn, Massachusetts, using liquid oxygen and gasoline. Back then, the local press barely noticed, but that quiet moment marked the dawn of a new era, one that would accelerate rapidly after World War II, when the US and the Soviet Union plunged into a fierce space race. Over the following decades, engineers pushed the limits of chemical propulsion, creating engines that would go on to become icons of space exploration. Think of America's mighty F-1, which launched the Saturn V to the moon, or the RS-25s that powered the space shuttle. There's also Russia's RD-180 on the Atlas V, and SpaceX's Merlin on the Falcon 9. But stealing the spotlight in this new era? The Raptor. SpaceX's cutting-edge engine built to take Starship to the moon, Mars, and beyond. Raptor is now considered the most powerful rocket engine in the world, thanks to its use of the full-flow stage combustion cycle, an advanced and extremely rare design. Unlike traditional engines that burn RP-1 kerosene or hydrogen, Raptor runs on the liquid methane and liquid oxygen. The latest version, Raptor 3, is a major upgrade over the already powerful Raptor 2. It's built to handle extreme chamber pressures, up to 350 bar. That means it can generate a staggering 280 tons of thrust, over 170 times its own weight, making it far more efficient than conventional engines. SpaceX's development of Raptor technology marks a huge leap forward, pushing the boundaries of what rocket engines are capable of. However, despite their immense power, chemical rockets come with inherent limitations, especially when it comes to exhaust velocity, the key factor that determines how fast they can push fuel out. This limitation makes chemical propulsion less ideal for long-duration interplanetary missions. Take the trip from Earth to Mars, for example, a journey of about 34 million miles that would take anywhere from 6 to 8 months using Starship's current technology. That kind of extended mission brings a whole set of challenges: prolonged exposure to cosmic radiation, microgravity, and the constant risk of micrometeoroid impacts. All of these pose serious threats to astronaut health. But luckily, there's one experiment NASA has been actively developing since the last century, one that just so happens to address many of the weaknesses of traditional chemical rockets: nuclear thermal propulsion. Before we dive into this mysterious engine, let's take a quick look at its rather unlucky history. NASA began researching nuclear thermal propulsion, or NTP, back in the 1950s with Project Rover, followed by the NERVA program from 1961 to 1973, a joint effort between NASA and the U.S. Atomic Energy Commission, which we now know as the Department of Energy. The NERVA program successfully developed and tested several nuclear thermal engines, achieving performance levels 3 times more efficient than chemical rockets. But despite its promise, the program was shut down in 1973 due to budget cuts following the end of the Apollo missions. Most of the funding was redirected to develop the space shuttle instead. Still, somehow, the research didn't completely die out. NASA quietly kept the dream alive, and in recent years, things have started moving again. In 2023 and 2025, new contracts were awarded to General Atomics and Standard Nuclear to continue development. And in January 2025, General Atomics successfully tested its reactor fuel at NASA's Marshall Space Flight Center. So, what makes this engine so special that NASA just won't let it go? Well, this technology has the potential to extract way more energy from a given amount of fuel, making it far more powerful and efficient. Dale Thomas, former deputy director at NASA's Marshall Space Flight Center, and now at the University of Alabama in Huntsville, explains that nuclear thermal or electric propulsion can pull significantly more energy from the same mass of fuel than traditional combustion-based systems. At its core, a nuclear thermal propulsion system works by using nuclear fission, a process where a neutron strikes uranium-235, turning it into uranium-236. This unstable isotope then splits into smaller fragments, releasing extra neutrons and a huge amount of energy. Today, over 400 nuclear reactors around the world use this same fission tech, most of them being light water reactors. These use water as a coolant to slow down neutrons and absorb heat, which is then turned into steam to spin turbines and generate electricity. But nuclear thermal propulsion systems are a bit different. They use specially designed fuel with a higher concentration of uranium-235, and they run at much higher temperatures. That makes them smaller, more compact, and way more powerful. In fact, they deliver energy densities about 10 times higher than conventional light water reactors. One of the biggest advantages? They can push fuel out at incredibly high speeds, creating massive thrust. This means rockets can accelerate faster and cut down travel time. On top of that, nuclear propulsion offers a much higher specific impulse, which is basically a measure of how efficiently a system turns fuel into thrust. Compared to chemical rockets, nuclear thermal propulsion systems have nearly double the specific impulse. Take SpaceX's Raptor 3 vacuum version, for example. It has a specific impulse of around 380 seconds in vacuum. In contrast, a nuclear thermal engine can reach around 900 seconds. That means we could cut the travel time to Mars almost in half, down from 6 to 8 months to just 2 or 3 months, maybe even faster. Pretty impressive, right? By the way, we're on our way to hitting 150,000 subscribers, and your support means the world to us. It's what keeps us going to bring you even better video every day. Thank you. Have you ever wondered how Starship would change if it were equipped with a nuclear thermal propulsion engine? Well, SpaceX would need to completely redesign the vehicle to integrate a nuclear reactor, one that uses uranium fuel in a ceramic matrix or graphite-based form, wrapped in special protective coatings, capable of withstanding extreme temperatures up to 3,000 Kelvin or about 4,940 degrees Fahrenheit. This reactor would heat a propellant, typically liquid hydrogen, to incredibly high temperatures, then expel it through a nozzle to generate thrust. And if SpaceX wanted to combine NTP with the current Raptor engines, Starship would have to carry 3 different types of propellant: methane and liquid oxygen for the Raptors, and liquid hydrogen for the nuclear system. That means a whole new set of cryogenic tanks, advanced insulation for the hydrogen, and a re-engineered structure to keep everything safe and efficient. In a typical rocket setup, a nuclear thermal propulsion engine, or NTP, is usually used on the upper stage, like Starship, rather than on the super heavy booster. That's because NTP generates less thrust than powerful chemical engines like Raptor 3. For a mission to Mars, for instance, the rocket might rely on chemical engines like Raptor 3 during liftoff to escape Earth's gravity. Once in space, it could then switch to the NTP engine for the cruise phase, taking advantage of its much higher specific impulse to dramatically shorten the journey. But while NTP holds a lot of promise, it's still going through rigorous testing, and for good reason. It's a powerful technology, but one that carries serious risks. That's why selecting the right reactor fuel is absolutely critical. Back in the day, General Electric and Argonne National Laboratory developed and ground-tested about 20 nuclear thermal propulsion engines. Those early designs relied on highly enriched uranium, or HEU, a type of fuel that's no longer viable because of its potential use in nuclear weapons. To address that risk, the U.S. Department of Energy and the National Nuclear Security Administration launched the Global Threat Reduction Initiative. The goal? To replace HEU in research reactors with a safer alternative, high-assay low-enriched uranium, or HALEU. Unlike HEU, HALEU contains much less fissile material, making it unsuitable for weaponization, an important step in ensuring nuclear propulsion stays safe and peaceful. And that's not even the biggest risk. One of the most serious concerns with nuclear thermal propulsion is the potential release of radioactive material if something goes wrong. And yes, it's a real threat. If a spacecraft powered by a nuclear engine failed during launch or in orbit, from debris impact, a design flaw, or a runaway reaction, the reactor could rupture, releasing radioactive fuel into the atmosphere or space and causing widespread contamination. These risks were one of the major reasons NASA shut down the Nerva-Osh rover nuclear rocket program in 1972, along with the fact that crewed missions to the moon were no longer on the table at the time. But hey, don't worry too much. It took scientists nearly 50 years to develop this breakthrough engine, and just as long to figure out how to make this dangerous energy safe. Now, it could be ready for real missions by 2030. Do you think this could really happen? Drop a comment and let me know what you think. If nuclear thermal propulsion becomes a reality, it could revolutionize space exploration. With faster travel times, spacecraft could reach distant destinations more efficiently, while reducing astronauts' exposure to long-term space radiation. Right now, Trump's budget proposal isn't final. Both chambers of the Republican-controlled Congress will draft their own version of NASA's budget, which must be reconciled before reaching the White House for the president's signature. So, there's still a glimmer of hope that the project might survive. With continued collaboration between NASA, DARPA, private companies, and top research institutions, the future of space travel is shaping up to be faster, smarter, and more ambitious than ever. Nuclear propulsion could very well be the key to unlocking the next great era of human exploration.